Hello, guys. So I had a few issues with recording of this video, which is just going over some problems of sound that are in Cengage and that will help you for the exam. I went over some examples in the video lecture, but there is a particular problem in Cengage where you have to be a little bit more careful. It's a problem where you have the bat and the insect. So I'm going to use similar numbers to what you have in the problem. So you have, let me just see how this looks. So, yeah. So you have a bat. I want to put it like that, flying at 5.25 meters per second. And it's chasing an insect flying in the same direction. So that's the thing. You don't know the speed. Let's call it V of the insect. VI. Be careful with the initial. It's just VI. V of the insect. The bat. So the bat emits a signal at 39, let's just say 40 kilohertz. And then it receives an echo which is at a higher frequency of 41.5 kilohertz. So there are different numbers than what you are giving in the problem. And the idea is to find the speed of the insect, taking the speed of sound as 343 meters per second. So this is a problem where you have to use the Doppler effect. And you have a moving source and a moving object. But the bat is receiving an echo. So you have to think in terms of the frequency received by the bat, which has to do with the reflective frequency. You see, the reflective frequency, let's call it F reflect, is equal to the initial frequency, and then you have the source moving, right? There. So why am I adding the VO? Because that will be this. So technically, that's this. The insect is flying away. But the source is going towards the insect. So the frequency reflect will increase technically because you're going towards the source, towards the object. The source is moving towards the object. So you have to include both. Now, since the bat or the insect is flying away from the source, technically you have that, right? The frequency, let's suppose the source was not moving. The frequency will decrease because the insect is flying away. All right. So then there is a second step where the insect is acting as the sound source because of the reflection. So you're going to have a situation where you have to calculate the returned frequency, F return. The F return is the reflected frequency. And remember, the insect keeps flying away. So that will be V plus V of the bat, if the bat is going towards, divided by V plus, well, plus the absolute value of the, well, basically, the speed of the insect. So let's explain this. First, the bat is going towards the insect. So you have this situation. Oh, by the way, let's say this is the sound. So, I don't want you guys to be confused. This is a bit of sound. There. So the reflected frequency will be the initial frequency, the speed of sound minus the speed of the insect over the speed of sound minus the speed of the source. So you have that. Good. But the returned frequency, which is this guy, 41.5, is the reflected frequency, which is this. So if you think about it, you are going to have the F return, the frequency that was returned, is equal to F reflected, which is the initial frequency, parenthesis, V speed of sound minus of the insect over speed of sound minus the source. Let's call this the bat. Now we can say it's the bat. And then you have, so this is this, and then you have to multiply by sound plus bat over sound plus insect. So it's not going to cancel, nothing's going to cancel. And that's good, because that shows that you are doing it right. Okay? So that's what you have to do. And over there, I want to calculate it. Now, F return is this. F naught is 40. So pretty much, you're going to have 41.5 kilohertz, which cancels with a 40, with a kilohertz there, 40, parentheses, 343 minus what you want to find. So 343 minus the insect over 343 minus 5.25. And then you have 343 plus 5.25 over 343 plus the of it. There you are. Yeah, perfect. You can see it. So there are some numbers there that we can calculate. For example, 41.5 over 40, that's 343 plus 5.25 over 343 minus 5.25. And then here you have 343 minus V of the insect over 343 plus V of the insect. Okay. So let's calculate this. 41.5 over 40, I get 1.04. 1.375. That's this plus that. That's 348.25 over 343 minus 5.25. That's 337.75. And here you have 343 minus VI over 343 plus VI. So let's calculate all this, all right? 1.0375 times 337 0.75, that's that, divided by 348.25. So I get 1.006. That's 343 minus VI over 343 plus VI. So if I multiply this, I make it equal, so I will get 343 times 1.006. I get 345.06 plus 1.006 VI equals to 343 minus VI. So I get 2.006 VI equals to, what happened here? See, because of the frequencies, probably put the wrong numbers. Let me see. Yeah. Yeah. Maybe the frequencies I gave is giving me a negative number here. Let's see. Let's see if it makes sense anyway with magnitude wise. $343 minus 345.06. Divided by 2.006. Yeah, I get 1.02. You get 1.02. 1.026. So yeah, so it's eventually gonna catch the insect. But that's basically the procedure. I think what makes this problem hard is the double Doppler effect that you have to worry about. First, you have to do it with respect of the insect, then you have to do it with the bat and the insect. So this is the bat. So insect, bat, insect. All right. That's basically what you had to do. It's a more difficult problem. Okay. Let's do a pipe problem. I don't know if I did enough in the video lecture. I'll leave that in there so you guys can take a look at all that math. A pipe open at both ends. So you have a pipe, remember that if it's like that, then it goes like this. Right? Or if you think about it, the fundamental frequency is n over 12 times the speed of sound. So it says that the fundamental frequency is equal to 370 hertz. That's for n equals to 1. What's the length of the pipe? Easy. 1 over 12 times 343 equals to 370. So L will be 343 over 370 divided by 2. So 343 over 370 divided by 2. That's about 0.46 Well, that's assuming the speed of sound to be 343. Remember that it can change depending on the temperature. And if they were asking you to find the frequency at the second harmonic or the third harmonic, you just change the value of n. All right. So there is not much for sound besides this. There is another interesting standing wave problem here, where they tell you that the distance of a distance of 5 centimeters is measured between two adjacent nodes of a standing wave on a 25 centimeter long string, in which harmonic is the string vibrating, and they give you 5 antinodes. So standing waves, just so you know, they are waves that look like this. So 1, 2, 3, 4, 5. And then here you have 1, 2, 3, 4, 5. These are the nodes. I want to use another color. These are the nodes, 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 nodes. And these are the antinodes. So you are in the fifth harmonic. So n equals to 5. Easy. And find the frequency of this harmonic if they give you the mass and the tension of the string. Okay. So they give you the distance between two nodes, which is 5 centimeters. So this is 5 centimeters. All right. And the length of the rope, the length is of 25 centimeters. So if you want to find the frequency of that node, just like, so now we can go with this. The frequency is n over 12 square root of 4 divided by mu. So n is 5. The length of the rope is the 25 centimeters. And the force, they give you a tension here of 900 newtons. And the mass, so they give you the mass of this rope equals to 2.1 times 10 to a negative 2 kilograms. What do you do that? So you can calculate the mu. Mu is equal to mass over length. All right. So mass over the length, 0.25. That will be 8.4 times 10 to a negative 2. That's kilograms per meter. So that number goes here. So you just have to calculate that. This is 0.5, this is 10. All this will be 10 times 930. Huh. 10 times 10 divided by the square root of 8.4. Let's see what's the square root of 8.4. It's 2.9. So 3,000 divided by 2.9. About 1,034. Yeah, there you are. 1,034 times. That's the frequency of the vibration in the fifth harmonic for this rope. Let's go on the Doppler effect. I want to make sure that's clear. I think standing waves, sound waves in pipes is just applying the formula, either if it's an open pipe or a closed pipe. Doppler effect requires a bit more of thinking. All right. So let me show you. I haven't shown you that problem. I mean, you have them in web assigned, but let's take a look at the following. Yeah. So you have an airplane traveling at half the speed of sound, so half of 2 or 343, and emitting a frequency of 5.25 kilohertz. At what frequency does the stationary listener hear the sound as the plane approaches? So I went over kind of over that in the video lecture, but there are two situations there. One when it's approaching, one when it's leaving. And that's important for the signs in the Doppler effect. Now, I always recommend students to think logically. Meaning, if you have the airplane coming towards you, so this is you, the frequency that you are going to listen is going to be greater. Now, the listener is not moving. And the frequency emitted by the airplane, as you read it, the initial original frequency, FO, is 5.25 kilohertz. But you're not moving. It's the source that is moving. If the source is moving towards, then the frequency prime is the original frequency. And then what you're writing here is speed of sound over speed of sound minus the speed of the airplane. Well, this is half of 343. Why nothing here? Because the observer, you are not moving. If you were moving towards, you will be plus. Remember the insect, right? In the insect problem, that was minus because the insect was moving away. Well, in one of the frequencies, right? The return in the reflector. So F0 is 5.25 kilohertz multiplied by 343 over 343 minus half of the airplane speed, which is 171.5, of course. What? That will be 2. This is 2. Because 343 minus 174 minus 175.5 is 175.5. 343 is double 171.5. So all the parentheses is 2. 2 times 5.25 is 10.50. So 10.50 kilohertz is double. Makes sense because the airplane is traveling at very high speed. In the insect problem, the difference between the speeds was not very large. So that's why the frequency reflected and the original frequency, the difference was little. Here you're talking about a double difference because we're talking about an airplane moving at half the speed of sound. There you have it. Now, what happens if the airplane now is here, moving away? So this is when the airplane is approaching. Now, when the airplane, so let's put yourself here. Again, you're not moving. So the airplane now, you are going to record or listen a lower frequency. F prime is the original frequency. Parenthesis, speed of sound over speed of sound plus the speed of the airplane. That's the difference. It's going to be lower the frequency. 5.25, 343 over 343 plus 171.5. Half, right, of that. So that will be 2/3. Because it will be 1 over 1.5. Right? So it's 2/3. So the value will be 2/3 of that. 3.5 kilohertz. Everyone. So that sound not bad. I mean, now we can start moving into light and electricity. That's gonna be on the next video. All right. See you guys later.